I want to give an intuitive derivation of how Einstein's field equations in vacuum can be derived from a string theory. We start from the Polyakov action, written in the following way: S equal to minus 1 over 4 pi alpha prime integral d squared sigma g mu nu d alpha x mu d alpha x nu, where in this case here I have the following: d alpha x mu d beta with a lower beta x nu era alpha beta. So here I'm assuming that I have the Lorentz metric, and remember that mu and nu go from 0 to 25. If we change the time component from x0 to I x0, the metric g mu nu will become the Euclidean metric when we have a flat space. So in general, when we have a flat space, g mu nu will go to era mu nu, so the Lorentz metric. But if we make this transformation here, it's simple to see that we actually get a Euclidean metric delta mu nu. So this is a Kronecker delta. And I will show you why also in the following, because we can also rewrite the integral by changing the variables tau and sigma to I tau and sigma. So sigma is left unchanged, whereas tau goes to I tau. I, of course, is the imaginary unit. In this case, the metric changes from era alpha beta to delta alpha beta, because the invariant element, the s squared, can be written as minus d tau squared plus d sigma squared, and this can be written as d I tau squared plus d sigma squared. So in the new variable, we actually have the Euclidean metric delta alpha beta, and this is just for convenience. Now we want to expand the tensor g mu nu here, this tensor near the origin, such that g mu nu, which depends on the fields, and when I say the origin, I'm assuming that all the fields are 0, so that's what I mean. This will be approximately equal to, let me write an equal sign, delta mu nu plus beta, which is just a constant. Then here I have the Riemann tensor R, mu lambda nu gamma, which is evaluated at the origin, so I can put 0 here to remind me that this is evaluated at the origin, but in the following I will not put the 0 here. And then here I have x lambda x gamma, like this. So we are summing over lambda and over gamma. And let me explain this a little bit more. So notice that since we are near the origin, g mu nu will be approximately equal to delta mu nu, and this makes sense. It's as if we are considering local coordinates, thanks to which we can make the metric flat. With this choice of coordinates, we see that the derivatives of the metric are 0 at the origin, because if you take the derivative of this expression, it will not be quadratic in terms of these x components here, but it will be linear to the x components, and when you set the x component to 0, you will get that the derivative of the g mu nu will be 0, right? And so also the Christoffel symbols will be 0. On the other hand, the second derivatives of the metric should be proportional to the Riemann tensor, so it makes sense to think that such coordinates exist, despite we did not prove it rigorously. But if you recall from General Relativity, we often assume that the Christoffel symbols were 0 because we were using a local frame, whereas the Ricci tensor or the Riemann tensor, they were not 0, but its expression would simplify. So it is something related to that. Now, the action becomes S equal to minus 1 over 4 pi alpha prime integral d squared sigma. So I'm simply replacing g mu nu with this expression here. So we have delta mu nu d alpha x mu d alpha x nu plus beta. Then of course I have the Riemann tensor r mu lambda nu gamma x lambda x gamma, and then I have d alpha x mu d alpha x nu, like this. Now we will focus on this term here. So this term here is related to 26 independent scalar fields. If we only look at that part, it would lead to a free wave equation with the mass of the particle being zero, right? It's something that you can understand from this part of the action. To see how the particle evolves, in quantum field theory we take the vacuum expectation, or the so-called propagator. We have something of this kind: 0, x mu of sigma alpha, x mu of sigma tilde beta acting on the vacuum here. And remember that in general, also from quantum field theory, we might have a time ordering to be rigorous. But anyway, if we put this expectation in the wave equation, which we write like this, d alpha x mu, so the wave equation will be equal to 0. But in order to find the propagator, we set it equal to delta, so the Dirac delta of sigma alpha minus sigma tilde beta, like this. And let me just write it like this: delta of sigma minus sigma tilde, for simplicity. Now we can write this expectation by expanding it like this in a Fourier series: d squared k over 2 pi squared. So we have to integrate over d squared k, e to the I k dot product with sigma minus sigma tilde vector. So we take the dot product between these two vectors, and then here I have a function f of k. When we take the derivative, this derivative here, and in this case you have to think that instead of x mu we have this vacuum expectation, and in particular these derivatives here are performed with respect to the variable sigma alpha, so they will act on this term, and I'm just trying to explain it intuitively. So when you take these derivatives, you will get a factor of minus k squared, because you will have to take the derivative of the complex exponential. And in order to get a Dirac delta, because remember that the second derivative should be equal to the Dirac delta, we have to set f of k equal to minus 1 over k squared. And with k squared here, I mean the mode squared of this vector here, k1 and k2. These are the conjugate variables, so k1 and k2 are the conjugate variables with respect to the sigmas. So in this case, the conjugate variable to this sigma here. They have sigma 1 and sigma 2, or sigma 0 and sigma 1, and they are tau and sigma. And in this case, we are considering a Euclidean metric, so it's as if we had the variables I, tau, and sigma. Anyway, this is not a problem. It's something technical, but I just want to give you the intuition without being too rigorous. So we can write the vacuum expectation like this: x mu sigma, x mu sigma tilde, and here we have 0, equal to integral d squared k over 2 pi squared e to the I k dot product sigma minus sigma tilde vector, and then we divide by minus k squared. This is the propagator for a boson. The problem with this integral is that it does not converge. we can see this with a trick which is called dimensional regularization. Let me write it down. Dimensional regularization. Namely, we have to rewrite the integral, this integral here, instead of 2 here, we are going to replace the 2 dimensions with 2 plus epsilon. Here we have 2 plus epsilon, like this. So this will remain the propagator because it comes from the wave equation, and we leave it like that. But we think of k as a 2 plus epsilon dimensional vector in this case. So this is the only difference. But here we are left with the k squared. So this is not k to the 2 plus epsilon. It will remain k squared because it comes from the differential equation here. So this second derivative will remain a second derivative. And we should think of epsilon as some integer in general at first. But after the calculation, we will let epsilon go to 0. So this is a mathematical trick because it doesn't really make sense, right? When you think of a dimension in general, it should be an integer. But this is what is done also in physics to understand something about these expectation values and how these integrals diverge, because we want to understand how the integrals diverge and if we can find a way to renormalize our theory. If we use generalized polar coordinates, this integral can be written like this. So we have an integral over d omega here, and this is just the generic solid angle element. It's related to the solid angle. So in general, if you had only 2 dimensions, it would be d theta. It would be just one angle d theta, right? It's as if you were using polar coordinates in that case. Then here we have 2 pi, 2 plus epsilon, and then we have k to the 1 plus epsilon dk. So if epsilon were equal to 0, here you would have k dk, which would be related to the polar coordinates, right? Because when you go to polar coordinates in 2 dimensions, you have k dk d theta, or in this case it would be d omega, like this. And in this case, we should think of this k here as the mode of this vector here. So it is related also to polar coordinates, because with polar coordinates, if this is the vector, the variable that we usually call rho or r will simply be the square root of the components here, k1 squared plus k2 squared. And if we have more dimensions, this can be generalized, and it would have this form here. So this d omega would be more complicated. For example, think about spherical coordinates. You would have an element of solid angle, and then here you would have k squared dk in 3 dimensions. So because k1 plus, in this case, we would set epsilon equal to 1, so we would have k squared dk. And in polar coordinates, if you recall, you have something like r squared dr, then you have sine of an angle, sine phi d theta, something like this. And this would be the element d omega. And this could be generalized to higher dimensional spaces. Then we divide by minus k squared. We have e to the I, and I'm going to rewrite this dot product here in this other way. So we can write the dot product as the mode of the first vector. Then we have the mode of the second vector, which is sigma minus sigma tilde vector, and we take the mode of this. And then we have the cosine of theta, which is the angle between the vectors k, this vector here, k, and this other vector, sigma minus sigma tilde. Now, don't be scared by this, because we are only interested in understanding how the integral diverges. So we don't want to do a full calculation of this. This is, in any case, this is equal to, we can write it as, so we have the integral over minus d omega divided by 2 pi 2 plus epsilon. Then we have another integral over this decay from 0 to infinity, because it's a magnitude, so we can integrate it from 0 to infinity, k to the minus 1 plus epsilon. So I'm putting these two together. So I get minus 1 plus epsilon e to the minus ik mod of sigma minus sigma tilde. And then here I have the cosine of theta dk. I'm putting dk here. Now we can rewrite this integral here. In particular, we will make a substitution, so we will set x equal to k mod sigma minus sigma tilde cosine of theta. And if we make that substitution, the integral can be written as 1 over mod of sigma minus sigma tilde to the epsilon. Then we have cosine to the epsilon of theta. This is raised to the epsilon. And it simply comes from this substitution, as I said, because dk would be written as dx divided by this constant. And then k to the minus 1 plus epsilon would be written as x to the minus 1 plus epsilon. Then this constant here would be in the denominator raised to the minus 1 plus epsilon. But the minus 1 will be cancelled by the plus 1 that you get from here. So you get this denominator raised to the epsilon, which is a constant, and you can take it out of the integration. Then you have an integral from 0 to infinity of x to the minus 1 plus epsilon e to the minus ix dx. Now, it is possible by using complex calculus, and I have put a derivation in the appendix. So you can check out the derivation in the appendix. By means of complex calculus, when epsilon goes to 0, you can show that this integral can be written as an integral from 0 to infinity of x to the minus 1 plus epsilon. And here, instead of the complex exponential, you can put a real exponential e to the minus x dx, and you get an additive constant plus I pi over 2. So you can show with complex calculus that this integral is equal to this when epsilon goes to 0. And as I said, you can check out the derivation in the appendix. But now at this point, this integral here is familiar, should be familiar to us. This is the gamma function evaluated at epsilon. So this is just gamma of epsilon plus I pi over 2. And the discontinuity or the divergence comes exactly from this, when we let epsilon go to 0. So let me write it here. So this vacuum expectation of x mu sigma tilde is proportional to gamma of epsilon. And when epsilon goes to 0, we will see how to rewrite this gamma of epsilon. I will show you also the derivation in the appendix, because I will not do it in this video. But first, let me tell you that since the fields are independent, if we change, for example, this mu to nu, the only difference here would be that this would be proportional also to delta mu nu. So this would be the only difference. This is the Kronecker delta. So when mu is not equal to nu, you will get 0 here. And gamma of epsilon, when epsilon goes to 0, can be written as 1 over epsilon minus gamma. And gamma here in this case is the so-called Euler-Mascheroni constant. And as I said, I will put a derivation of this other expression in another video in the appendix, so you can check it out if you're interested. Now, therefore, as epsilon goes to 0, we get a divergent term, which is proportional to delta mu nu. So this is proportional to delta mu nu over epsilon. And I'm just considering the divergence. So because we are interested in the divergence, so we realize that when we take the vacuum expectation of these variables the x variables, so x lambda and x gamma here. When we take the expectation, for example, of these two variables, we will get a divergent term which is proportional to 1 over epsilon, so delta lambda gamma over epsilon. If we want to remove the divergence, we have to substitute, we have to replace x mu x nu with x mu x nu minus the vacuum expectation, x mu x nu, like this. By doing so, if we replace this, basically we are putting that in here. So in this case, instead of mu and nu, we have lambda and gamma, but it's very similar. So if we do so, the term r mu lambda nu gamma x lambda x gamma d alpha x mu d alpha x nu will be replaced like this. So r mu lambda nu gamma, here we have x lambda x gamma minus the vacuum expectation, which is proportional to that divergent term. So we are going to put the proportionality constant, lambda, and then we know that we get delta lambda gamma divided by epsilon. So maybe this constant here should not be called lambda because it could be confused with this lambda here in the Kronecker delta. But try to bear with me, so this is not a problem because this is just a constant, whereas this lambda here we are summing over this other index lambda. And then we have d alpha x mu, d alpha x nu, and this can be written as r mu lambda nu gamma x lambda x gamma d alpha x mu d alpha x nu minus lambda over epsilon. And then when we multiply this delta lambda gamma with the Riemann tensor, we sum over lambda and over gamma, we get the Ricci tensor r mu nu d alpha x mu d alpha x nu, like this. So basically, with this renormalization, the metric g mu nu will change to g mu nu minus a constant called lambda prime over epsilon r mu nu, where lambda prime is simply equal to lambda times beta. So it's this lambda here multiplied by the other constant that we had in the action, and if you recall, we add beta here. So that's just a constant. It doesn't really affect our reasoning. So you can easily understand, if you followed these steps, that the g mu nu should transform like this. So we have to change the g mu nu to this if we want to remove the divergence. That's the importance of these steps. Now let's start from the normalized action, the renormalized action, and let's rewrite it. So s equal to minus 1 over 4 pi alpha prime integral. Now we want to use dimensional regularization also here. So we have d squared, instead of d squared, we have d2 plus epsilon sigma. We will use the dimensional regularization. I want to show you why. So we have this plus epsilon here. G mu nu minus lambda prime over epsilon r mu nu d alpha x mu d alpha x nu. Then we will let epsilon go to 0. Now let's make a while transformation. Remember the while transformation. So we change from the metric delta alpha beta. So remember that we are using the metric delta alpha beta instead of the Lorentz metric eta alpha beta because we have changed the coordinates. So we are using I tau and sigma. We can use this metric. Remember that this is a 2 by 2 tensor. Do not confuse this type of tensors with the 26 by 26 tensors of space-time related to the indices mu and nu. So we are changing from this metric to e to the 2 phi delta alpha beta. So we are making the Weyl transformation, and therefore we can multiply the metric by this factor. So if we want to rewrite the action, remember that this will be some new metric g alpha beta. So this is our new metric. In the action, when we change the metric, we will have something of the kind square root of g. So we have the square root of the determinant of this matrix. So we don't have the minus sign here because now we're using a Euclidean metric. So the determinant will be non-negative. And this is multiplied by g alpha beta. So if we calculate the square root of g, we have the square root of e to the 2 phi, which is raised to the power 2 plus epsilon, because now the matrices will not be 2 by 2, because they will be 2 plus epsilon dimensional, because we are using dimensional regularization. So strictly speaking, these tensors are 2 plus epsilon dimensional, those with the alpha and the beta. So here we are raising this to the 2 plus epsilon, then the determinant of delta alpha beta will be 1. So this is what we get. And from here we can write this as e to the 2 phi times e to the phi epsilon. And g alpha beta with upper indices can be written as e to the minus 2 phi delta alpha beta with upper indices. So when you consider the square root of g multiplied by g alpha beta, this will be equal to e to the phi epsilon times delta alpha beta. And since we will let epsilon go to 0, this is approximately equal to 1 plus phi epsilon delta alpha beta. Now let's rewrite the action. S is equal to minus 1 over 4 pi alpha prime integral d2 plus epsilon sigma. Here we have the metric g mu nu minus lambda prime over epsilon r mu nu. This is after renormalization. And then we have the contribution due to the Weyl transformation, 1 plus phi epsilon delta alpha beta. And then we have d alpha x mu, d beta x nu, like this. And now you can also rewrite it in the following form, in the following fashion: minus 1 over 4 pi alpha prime integral d2 plus epsilon sigma g mu nu minus lambda prime phi r mu nu minus lambda prime over epsilon r mu nu delta alpha beta d alpha x mu d beta x nu. Now notice that when epsilon goes to 0, well, we know that this term will diverge, but we have motivated this term by means of renormalization. We need this in order to renormalize the vacuum expectation, for example, right? That's what that's how we motivated it. But then we also have this term, which depends on phi. But this term here would break Weyl invariance if it were not equal to 0. The Polyakov action should be Weyl invariant. In order to restore this fundamental invariance, we have to set r mu nu equal to 0. So that's the only possibility, r mu nu equal to 0. Because lambda prime here is just a proportionality constant that we don't have any degree of freedom on that. But we can set r mu nu equal to 0. So we are forced to choose r mu nu equal to 0. And this is a magical result. This means that the background spacetime in which the string moves must obey Einstein's equations in vacuum. This is a 26 by 26 tensor, and at this point you might think, well, we live only in 3 spatial dimensions, so how can we make sense of this? A higher dimensional world could be reduced to a lower dimensional one if we think of quote-unquote curling up extra dimensions to a small size. For example, take a donut, or if you want to be more rigorous, a torus, and think of reducing its cross-section to zero. It will become a wire, so it will be one-dimensional. Now take the wire and squeeze it down to a point. And this is how we start from a two-dimensional object, a torus, and we get to a zero-dimensional one, a point. So we need to think about these dimensions which are curled up in order to start from a higher dimensional space and go to a lower dimensional space, so that we could make sense of this also in three spatial dimensions.